morning. Mr. Lesham is here, and we are continuing with calculus. We're going to learn about the second derivative today, and we're going to use it. Okay, we're going to use it for something called concavity. Okay, so let's start with a function. Okay, f of x. Oh, that should be 3x cubed. Okay. As you noticed already from yesterday, I'm kind of tuning in all the functions I'm using are cubic function, because eventually we're going to use all the stuff that we've been learning and explore cubic function, learn how to draw them, learn how to find all sorts of stuff about it. So let's find the first derivative. What's will be the derivative? Let's call it the derivative. Okay? What's the derivative of this? No, that should have been x cubed, not 3x cubed. Yes. Good, right? 3x squared minus 10x plus 3. Okay? We'll call that. Yeah, we're right?
So you left the x and 10.
I left the x, you're right. Okay? So this is what we call the first derivative. We'll call that the function. Okay? So if the function is that, that's the first derivative. Now, okay, I've never really used the first derivative. Why am I using the word first derivative? Because there could also be a second derivative. Okay? Second derivative. And a third, you're right. Derivative. Okay? So, I mean, what does that mean? Like, the first derivative in itself is a function. Okay? It's something of x. So, nothing stops us to find the second derivative. The second derivative, okay, I would personally, and they do it as well, so I'm glad, we simply put another prime to just show that we do another derivative. But what we do in derivative of the first derivative, right? The second derivative is the first derivative, or the second derivative is the derivative of the first derivative. But we use the same, it makes sense. We use the same rule. What will it be the second derivative?
I would say
just a bit louder. 6x minus 10. Okay? So something interesting happening as we go, if we work with polynomials, okay? And in high school we're only going to work in polynomials, okay? Okay? As we go on from the function, which is order 3, to the first derivative, which is a quadratic, is order 2, and the second derivative is just a linear function. Okay? So the order goes down. I'll just pause for question. So now, and somebody asked me, Ollie asked me, can we carry on to the third derivative? We can, but we're not going to do it in high school. Okay, so don't have to worry about it. And to be honest, the third derivative, you don't often use it. Really, it's not something we will use a lot. Okay, what we're going to try and do in the rest of this lesson and give meaning to the second derivative. I mean, we already know what's the meaning of the first derivative. What does the first derivative tell you? If, let's say, the first derivative is positive, what do you know about the function? The first derivative is positive, the function is? No, you don't know if it's negative or positive, but the first derivative, remember, first derivative is your gradient. So if the first derivative is positive, the graph or function is increasing. Remember, that's what we did last lesson, wasn't that long ago? Okay? Thank you, Ted. Okay? If the first derivative is negative, then the graph is decreasing. Do you remember that? Okay, so now we're going to try and give meaning for the second derivative. And to do that, we're going to look at a function. I told you that a graph, or a typical graph of, what do you call it? Cubic function looks like this. Okay? So now we have two areas. We have this area and that area. Okay? The blue area and the red area. When we have something like this, like you can say a ball, I don't know, not a ball, you know, a ball that you eat from, okay? Something that goes down, then up, okay? This whole area, if we say it's concave up, this is the idea of concavity, okay? Graphs have concavity. They have gradients, but they also have concavity. If it goes like this, it's concave up. If it goes like that, it's concave down. Okay? So for example, if I divide this bit here, you can see that the first part here, it's concave up. Concave up. And on the other side of this line, it's concave down. You understand what I'm saying about concavity? Yeah? Now pause. Good question here. Okay, again, concavity doesn't mean go up or down. Because if I look to the left of this line, it goes down here, but it goes up there. But what I'm saying in both places, all over here, okay, it's concave up. It's like a part, any section part of it is like a section of a little ball. Okay? Where concave down, first of all it goes up and then it goes down, but everywhere here, if I just took a little small section of it, everywhere, yeah? Okay, shouldn't exaggerate. Here, everywhere it's concave down. It's like a part of a mountain, if that makes sense. Now what we're going to try and do is identify, I mean you look at the graph, you can say that's concave up, that's concave down, but looking at the function and decide when it's going to be concave up and when it's going to be concave down. That's all we're going to try and do. And first of all, I'm just going to tell you that, and then maybe I will be able to convince you why that is the case. As you can probably imagine, we're going to decide the concavity not based on the first derivative, but instead we're going to decide based on the second derivative. Otherwise I wouldn't have taught you that now, right? So anywhere where the second derivative is larger, so I'll put x, I'll put an x maybe. Oh, well, okay, let's put it, okay, let's do it like this. Let's do it like this, okay? This is, let's say x equal a. On this function, we're looking specifically at x equal a. Okay, so if the second derivative is larger than 0, then we know that the graph at this point is concave up. Okay? If the second derivative, at a specific point is smaller than 0, in other words, it's negative, then we know it's concave down. Okay? I'll just pause. So we will do it specifically with specific equation, it will make more sense. But what I'm just trying to kind of convince you that anywhere here, the concavity, or the second derivative is going to be larger than 0, and anywhere here, the second derivative is going to be smaller than 0. Okay? Now, before I try and explain it, maybe I can ask you, and you can probably guess, what will be the concavity exactly in that point in between, the transition from concavity up to concavity down? What will be the second derivative specifically here?
0.
It will be 0, you're right. Okay? If it's positive here, the second derivative is positive on this side, and it's negative on this side, well, if I have a positive number, yeah, then obviously at some point it will have to go to 0, and then it will pass and become negative number. Okay? So well done, Taylor, once again. Now, that point where the concavity changes, the graph changed from concave up to concave down, we call it point of inflection. Okay? That's a point of inflection. Okay? I'll let it sink a little bit and then we'll do examples. Just adding a little bit to it, just to make sure. Let's say, so we can choose a specific x. This is it, let's say x equal a. That means that the second derivative is 0. Okay? So if the second derivative is 0, then, and now I'm adding, it is possibly a point of inflection, but not necessarily a point of inflection. Okay? We will see examples later, but JD told me something yesterday which is along this line. That really means that every point of inflection, definitely then the second derivative is going to be 0. But if the second derivative is 0, it doesn't necessarily mean it's a point of inflection. Okay, we will see examples of that. Right, guys, so we are ready for our first proper example, and that example will make us understand what I was just talking about a bit better. So I've got another cubic function, and I drew it for you. Okay? Where is the point of inflection, by the way, by just looking at it? There's only really one option, what x is equal to. As x equal to -2. Can you see that this is the point of inflection? Before that, what is this? Concave up or down?
Okay.
That's concave up. And that means this is concave down. Okay? Just stress, guys, the concave up is not just here. It's here, it's here, it's here, it's here, everywhere up to x equal -2. The concave down is everywhere here, everywhere. And the point of inflection, as you guys already recognize from the picture, is x equal minus 2. That's where the concavity changes. Now what they're asking us is to determine by calculation whether f is concave up or down at x equal minus 3, x equal minus 1, and x equals 0, I think there. Okay? Now you already can tell me, I mean we know it, minus 3, what will be the concavity, up or down? Ah. At minus 1 it's going to be? Down. And at 0 it's going to be?
No. What's down?
Down. It's still down. It's still down.
No, it's in the...
But yeah, anywhere here. Shall I maybe do I'll do a change in color, okay? So anywhere from here, it's concave down. Okay? Concavity is not to do with if the graph is going up or down. No, it's to do with the shape of it. Okay? Mark, are you with us? Okay. So what's the first thing to do, as always in calculus? Find the derivative. Okay? Right, so it's going to be, I'll just do it quickly, okay? So minus 3x squared minus 12x plus 1. Okay? Now, whenever they ask you about concavity, then you need to also find the second derivative. Makes sense. Okay? It's in the title here. Okay? So it's going to be minus 6x minus 12. Alright?
So,
Just did it twice. Okay. Now, we want to find out the second derivative when x equal minus 3. So we just sub minus 3 in the second derivative. Okay? That's how we prove. Because we can't. They ask us by calculation to show the concavity. I started the question for you just by looking at the pictures, but that's not enough. They're asked to calculate. They're asked to calculate. It's not enough to say, oh, I can see it's concave. We must calculate the second derivative, assess it at minus 3. It's going to be minus 3, minus 6 times minus 3, minus 12, which is minus 30.
Minus 30? No.
No?
6, 12.
No, so it's negative.
It's plus, you're right.
Plus 6.
So it's plus 6. You're right. Which is larger than 0. Okay? So if the second derivative, minus 3, larger than 0, therefore it's concave up. Okay? That's how we prove concavity up or down based on calculation. Okay? We just can't do it from the picture. Okay? Same thing for x equal minus 1. Okay? For x equal minus 1, we'll just do the second derivative at minus 1. So it's minus 6 times minus 1 minus 12, which is 12 minus 12. I'm getting 0. Am I supposed to get 0? No, I shouldn't really get 0. I made another mistake. Yes. It's minus 6. Okay? So if the second derivative is smaller than 0, then it's concave. What is it, concave? Down. You can see it there. Concave down. Okay? And if I assess it at 0, the second derivative, so it's going to be minus 6 times 0 minus 12 is definitely smaller than 0. Okay? It's equal to minus 12, which is smaller than 0. Again, concave down. Okay? Alright, let's just see if you're alright with that. So now they're asking me to show that x equal minus 2 is a point of inflection. To show. Okay? So what do you reckon I need to do? How do I show it? I see it from the picture, but how do I do it? Well, I'm calculating second derivatives, right? So what should I do? Calculate second derivative at minus 2. Okay, let's see what happens. Minus 6 times minus 2 minus 12. This is 12 minus 12. It is 0. Okay? So if the second derivative is minus 2 is 0, can we say, I'll put it in question mark, can we say there is point of inflection? Can we say that? Okay? And because I put the question mark, the answer is probably no. Okay? Why no? Because if you remember, just before we start this example, I said something which probably most of you weren't sure what I'm talking about. I said that any point of inflection will have second derivative is 0. But it doesn't mean that every place where the second derivative is 0, it's a point of inflection, right? Giving you, what did you say, JD? You give me an example.
All thumbs are fingers, but not all fingers are thumbs.
Okay, all thumbs are fingers, but not all fingers are thumbs. It's the same thing, okay? Maybe let me try and draw it. If I draw, if I draw all the point of inflection, I'm going to call it what? The point of inflection, POI, okay? This is all the point of inflection in the world, okay? And now I'm going to draw all the ones where the second derivative, okay, I'll draw it like this. Second derivative equal to 0. That's all the places that have a second derivative which are 0. What does this diagram tell you? It tells you that, okay, so make sure everyone can see it. Okay, you can't see it. Everyone, you got the picture. Okay, all the point of inflections have a second derivative of 0. But there are places, there are second derivatives that are not point of inflection. So it's not enough just to show that the second derivative is 0. Okay, we need to do something extra. Okay, what do we need to do extra? We basically need to see what was the concavity before and what was the concavity after. Okay, what was the concavity before -2? Let's say at -1, what was the concavity before? The concavity was up, right? For x smaller than -2, the concavity up. For x larger than -2, for example, we looked here for -1, the concavity was down. So to prove, okay, I'll repeat, I won't write it down. To prove that a place, a suspected place is a point of inflection, I need to do two things. First, show its second derivative is 0. Second, I need to show that before that we have second derivative which is smaller than 0 and afterward it was larger. Or the other way around. Okay? I could have, okay, I know guys I'm kind of piling up here. Okay? In this case we have second derivative which was positive. Okay? And then we have second derivative which was negative. But we could have a graph like this. Okay? What will be the second derivative here? Positive or negative?
Be negative.
It will be negative. And the second derivative over here?
Positive.
It will be positive. So I'll maybe write it one time. Okay? No, I'm not going to write it. It's going to just, okay? Two things you need to show to prove point of inflection. One, second derivative is 0. Two, it's concave up before and concave down after, or concave down before and concave up after. Does that make sense? Okay? Cool. I'm just going to make some space and I'll show you one little thing before we move on. Before we move on to another example which will clarify it better, I just want to kind of show you why this is correct. Okay? What I claimed is that all the point of inflection have a second derivative of 0. But there are some second derivatives that are not point of inflection. Now there's all kind of examples, but the easiest example that I can think of is this. Okay? What does this graph look like? It's just a straight line, isn't it? It's a linear. That's the first kind of function that we talk about, right? It's a straight line. Does this graph have any point of inflection? Is there a place, a transition between concave? It doesn't have any concave up or concave. No, there's no concavity there. Okay, it doesn't look like, it's like this. It's this borderline, which actually I didn't talk about. It's this borderline, the concave up to concave down. There's no concavity. Okay, so if there's no concavity, it's no concave up or not concave down, there's definitely no transition. So there shouldn't be any point of inflection. Okay?
But that's not a derivative.
Well, that's not a derivative. Let's calculate the derivative. Okay? So what will be the first derivative? The first derivative?
Just
2. What will be the second derivative?
Nothing. 0.
Oh, not nothing. 0. So you see, this is a classic example where the second derivative is 0 for all x. Okay? So it's somewhere here, but there's no point of inflection. So just showing that the second derivative is 0 is not enough to prove that we have a point of inflection. You still need to show that it was concave up before. Let's say the second derivative is larger than 0. And then it was concave down. The second derivative is smaller than 0. Or the other way around. The second derivative is negative and then it becomes positive. Okay? Here, okay, the first derivative, if you look, for example, at the second derivative, is 0 everywhere. So we don't have that transition. Okay, I'll stop. Let's move on to example. Right, so guys, another example. We have another cubic polynomial, and they actually ask us find coordinates of point of inflection. Okay, what do we do? What do we start with?
Find the derivative.
Find the derivative. 3x squared minus 18x. I'll say it, but I want you to check me, okay? So I'm not making a mistake. Plus 3. Okay, what's next?
Find the
Second derivative. 6x minus 18. Okay, now here they didn't ask us to prove that a certain point is a point of inflection. They're asking us to find it.
So you make x 0 and y 0.
What should be 0? Something should be 0.
The
All of this, the second derivative, should be 0 for the point of inflection. So this is the second derivative for point of inflection. Okay, if second derivative is 0. In other words, 6x minus 18 is 0. In other words, x equal to 3, right?
Yeah.
Okay, so that's my point inflection. But is this enough? I was asked to find the coordinates.
Substitute x.
Substitute x, I need to find the y. Where do I sub 3? I have 3 things now. Where do I sub it?
Original.
The original function.
Original.
Because I want to find the y. Okay? So it's 3 cubed minus 9, 3 squared, plus 3 times 3 minus 5. And I'll copy their answer. They're getting minus 50. They're right. Okay? So in other words, the point of inflection, okay, we want to give coordinates. We spoke about it after, I think, test or exam. You got to be, you want to make the examiner on your side. So you got to be nice to him. You got to make it easy for him. Okay? If you just write 3 and minus 50 like this, the examiner will look and he won't even look at all that. So he'll say, oh yeah, you got it. And then you're going to get 4 marks. If you start writing x equal 3 here, y equal minus 50, then you make him go through everything. Okay? So be wise. Okay? Street wise. Okay? Right, we'll pause here. That'll be it for today. Bye-bye.